Okay, before we move to fluid dynamics and fluids moving, we're going to do one more example here. And the example says you need to determine the density of an unknown liquid. You notice that the block floats on this liquid. So you take a block and put it on this liquid, and it floats on the liquid with 4.6 centimeters submerged. So here's my unknown fluid. Here's the container. And here's the fluid. And the block looks like this. All right? So this is 4.8 centimeters. Okay? And by the way, the block will look like this. So it has a cross-sectional area A here. So the volume that's beneath the water will be the cross-sectional area times the depth. No, I'm sorry, this is unknown fluid. Unknown fluid. Then you place it in water. And you see that it also floats. 5.8 centimeters are submerged. So this is water here. So in water, it's the same cube or the same block. This is 5.8 centimeters. So it sinks a little deeper in the water. So we conclude that this fluid is denser than the water because it sinks less, because it needed to displace less of this fluid than the water in order for itself to float. We will see that. So this is this. Okay. So how are we going to do this? And so this is the cross-sectional area A here. So the block has a mass m. What are the forces on it? Of course, there is the mg here, mg, whatever the block's mass is, and then the buoyant force here from the water. And the same thing here, there is mg, and then the buoyant force from the unknown fluid, unknown density. Okay. So we can write down the following. We can say, all right, from here, the buoyant force from the water will equal to the mass of this block times gravity. And the same thing here, the buoyant force from the unknown fluid, I put U for unknown, will equal to mg, the mass of the block times gravity. That's how it would float. So this must equal to that. This is mg, this is mg. So the buoyant force from the unknown fluid will equal to the buoyant force from the water. Let's set them equal and see what happens. So here's solution. The buoyant force from the unknown fluid, is equal to the buoyant force from the water. All right. The buoyant force from the unknown fluid will equal to the weight of the fluid displaced, so that's the density of the unknown fluid times the volume of the unknown fluid times gravity. All right. Density times volume will give me the mass of the unknown fluid that was displaced times gravity, that's the weight of the unknown fluid displaced, which is the buoyant force by Archimedes' principle. Same thing here, the buoyant force that the water gives will equal to the weight of the water displaced, so that's the density of the water times the volume of the water that was displaced times gravity. And you notice gravity cancels. And so the density of the unknown fluid times the volume of the unknown fluid that was displaced. Since the box was submerged by a depth of 4.8 centimeters, let me call this one here depth 1, and this one here is depth 2. So the volume would be the depth times the cross-sectional area. Right? If you have here's what's beneath the water. It looks like so. If this is D1 and this is the area A, then this is the volume of that box that's below, and it has displaced an equal amount to its own volume. So the d1 times area, the area is the same, will equal to the density of the water times d2 times the area. Well, the area cancels on both sides. And so this will give me the fact that the density of this n-noun fluid will equal to the density of the water times d2 divided by d1. Okay. And you see it now. If d2 is larger than d1, then the material is denser. So this n-noun material will have a density of, the water is 1,000, and d2 is how far it's submerged in the water, that's 5.8 centimeters, and here it's 4.8 centimeters. Again, when you're dividing with the same units, the units cancel anyways. We don't need to change them. So we get the density of this n-noun fluid to be, let's get it, 5.8 over 4.8. I'm sorry, it's actually, I said 4.6, so let me just change it. Sorry about that. 4.6. 4.6 here. Yeah. Okay, good. So just a numeric thing. So we get, let me just write down the answer. It's 1260. 1260 kilograms per cubic meter. Okay. Well, I hope now you get this, and we're going to get to the fluids that are moving. So to do that, we'll set ourselves to the what's called the continuity equation. All right, just conservation of mass. All right, so to start with fluids flowing, we will take an ideal fluid. And an ideal fluid means basically the fluid means a few things. It's ideal if it's incompressible, as we have been assuming. The fluid does not change its density. We're going to assume the fluid is non-viscous, and viscosity is the fluid's resistance to flow. So our fluid is not going to have any friction. It's the resistance to flow comes from basically friction of the fluid with the walls of the container, and then we will just this model obviously has some limitations, because if you can have a fluid that's compressible and the flow could be turbulent, so we're going to say our fluid is ideal. All right, so that the calculations or the model is simpler. And as I always say, you always start with the simplest model you can get, and then you can add complexity to it. So for example, if you want to model the human body, you cannot just take every single molecule and try to model it and figure out where it is and then predict the motion and every psychology and physiology and everything. You will get nowhere. So if you want a model that includes everything, you got nothing. So you have to start with the simplest model you can, and then you can add complexity to it as needed, and you can modify your assumptions later on. Okay? So let's see. So fluid flow, fluid dynamics. So now our fluid would be moving, right? So here is a fluid, let's say here, it's flowing on a pipe, So the fluid is flowing here. Let's say it has a speed v. Let's call this one v1. And let's say it's going through a cross-sectional area here, a1. This is a1. And the fluid here will have possibly a different speed called v2. And the area here is a2, right? a2. So you get V2 and A2 here at the top, and V1 and A1 at the bottom. I'll come back to this in a moment. So now I want the relationship between V1, A1 and V2, A2. I think you would agree that if 1 kilogram of fluid passes this way, 1 kilogram has to get out. And then since the fluid is incompressible, we can say the volume of fluid that comes in has to equal to the volume of fluid that comes out. So if you have a drain, if you're putting 1 gallon in, 1 gallon has to come out in the same amount of time. So if you're pumping 1 gallon per second, 1 gallon per second has to come out from the other side. So the volume from this side has to equal to the volume from that side per unit of time. So let's see. So if you allow after an amount delta t, the fluid that was here will fill out this volume now. Let me call this one here delta x1. And delta x1 will just be the speed of the fluid here, v1 times delta t1. So imagine you close your eyes, it will fill out this much. It will fill out this much of this pipe, right? Imagine this is, so as it flows, you ask how much flowed in 1 second. Well, it's equal to the area times the length here. So the volume, delta volume, V is the volume, not velocity here. I'll put like bars like this to distinguish it. Delta V will be the area 1 times delta x1, and so and that is equal to area 1 V1 delta t, and so delta V1 over delta t, we call this amount here Q. So if you divide both sides by delta t, you get A1 V1. How about from the other side? Let's see what the flow is. From the other side, in an amount delta t, so the fluid was here, now it is here, so it has filled out this much. So this is V2 times delta, let me call it delta x2. So delta x2 will equal to V2 times delta t. And the area here is A2, so the volume, delta volume here 2 that has flowed, will be A2 times delta x2, and so, and that is equal to A2 V2 delta t. And so this amount of fluid flow, let's call it Q2, and this one I'm calling Q1 here, they would be equal. Delta V2 delta t, that's delta volume, delta t would be A2 V2. So the area times the cross-sectional area times the speed is the volume per unit of time. How much fluid is flowing in per unit of time? How many gallons per second are you getting in? And that has to equal to how many gallons per second that's coming out. And so we say the flow rate Q1, which is A1 V1, has to equal to Q2, which is A2 V2. Continuity. It comes from conservation of mass. And if the fluid is incompressible, you will get conservation of flow rate, volume per unit of time. Let me just say what it implies is A1 V1 equals to A2 V2, and that quantity is called Q. All right, that's what we need. Now, this quantity Q is the volume flow rate, and we will need it in a moment when we derive Bernoulli's principle. Okay, just as a quick example, so suppose you have like a 20 meter wide, 20 by 4 meter, 20 meter wide, 4 meter deep river, and then with triangular cross section, right? So you have the river looks like this. Let me show you here. Let's say it's a triangular cross section. It's 20 meters wide, and then it is I think I said 4 meters deep, and the water is flowing this way. It's flowing this way. Let me just make sure that it is. Yeah, it's 20 by 4, and it is flowing here at a speed of V1 equals to 1 meter per second. All right, so you have a river that's flowing like that, and then as it makes its way to the sea, it enters an area where the width is 4 meters and the depth is 6 meters, and it's still triangular, so it's 4 by 6. So you have now 4 meters by 6. Kind of narrows down. So you see here it's a bigger area, here it's a smaller area. You see if the area gets larger, then the speed drops. If the area gets smaller, then the speed increases, because this product and this product, they have to be equal. So we say V1 area 1 equals to V2 area 2, and so V1 is 1 meter per second. Area 1, well, area of a triangle is half the base times the height, so 1/2 of 20 times 4. That's the area 1, and then V2, I'm trying to find it. And then for area 2, it's half the base times the height, so 1/2 of 6 times 4. The 4 goes away, and we get, oh, and the 1/2 also goes away on both sides. So you get V2 will equal to, I guess, 20 over 6, which is 3.33 meters per second. All right. I want to move on now to Bernoulli's equation. Okay. So for Bernoulli's equation, I think I don't have enough time to do it in this video by itself. So I'm going to pause this and then go to the next video and start it.